Hey everyone, welcome. Today we're going to dive deep into a really cool concept from calculus it's kind of hiding in plain sight. It powers everything from how we engineer sound to how we compress data. We're going to crack open the idea of orthogonality, which sounds complicated, I know, but it's a surprisingly simple idea with the power to unravel some incredible complexity.
All right, let's kick things off with a huge question. Look at a really messy, complicated-looking wave. Like the sound of a full orchestra or some jagged signal coming from a sensor. How in the world could you break that down into simple, predictable, manageable pieces? It seems almost impossible, right? Well, it turns out math has this incredibly elegant answer.
And that answer? It's called the Fourier series. This is the mathematical tool that lets us do exactly what we just asked. It allows us to take a really complex repeating function, like a sound wave, and rewrite it as just a sum of simple sines and cosines. This quote right here, it basically gives away the whole secret in one sentence. The entire magic trick, the whole thing, hinges on this one single word, orthogonal. But what does that even mean when we're talking about functions and waves, and not just, lines on a piece of graph paper? So, to get our heads around this, we're actually going to start with something you probably already know from geometry, vectors. Believe it or not, this analogy is the key that's going to unlock this whole concept for us. So check this out. This slide builds a perfect bridge between these two worlds. In geometry, right, we all learn that two vectors are perpendicular if their dot product is 0. They meet at a perfect 90-degree angle. Well, for functions, the core idea is exactly the same. We just use a different word, orthogonal. And the test? It's shockingly similar. Instead of a dot product, we use something called an inner product, which is really just a fancy way of saying we multiply the functions together and add up all the results over a specific range using an integral. And here's the cool part. Just like with vectors, if that integral, that inner product, equals 0, the functions are orthogonal. Okay, so let's make this test official. We need the actual tool, right? The mathematical machine we can use to figure out if any two functions are orthogonal. And here it is. This is the formal test. But honestly, the idea is super simple. You take two functions, we'll call them f of x and g of x, and if the integral of their product over some interval is exactly 0, that's it. If the result is a big fat 0, they're orthogonal. If it's anything else, they're not. Simple as that. All right, that's enough with the theory. The only way to really get this stuff is to see it in action. So let's put a couple of pairs of functions on trial, so to speak. We'll run them through our new orthogonality test and see what happens. So first up, we've got a pretty straightforward pair of polynomials. The function f of x equals x, that's just a straight line through the origin, and g of x is equal to x squared, a classic U-shaped parabola. The question is, are they orthogonal on the interval from -1 to +1? Let's find out. Okay, so how do we run the test? We just follow the formula, we multiply the functions together, which gives us x cubed, and then we integrate that result all the way from -1 to 1. And the verdict is, yes, they are orthogonal. The value of this integral is 0. Now, why does that happen? It's because x cubed is what we call an odd function. If you look at its graph, it has perfect rotational symmetry. That means over a balanced interval like this one, the negative area under the curve on the left side is an exact mirror of the positive area on the right. They just cancel each other out completely. So, test passed. All right, time for the main event. This is the case that really matters, the one that brings us all the way back to our original problem about waves. Are the fundamental building blocks themselves, sine of x and cosine of x, orthogonal to each other over the interval from -pi to pi? You know the drill by now. We set it up in exactly the same way. We multiply sine of x and cosine of x together and integrate that product from -pi to pi. The result of this one calculation is the key to our entire mystery. And the answer is a huge yes. This integral evaluates to 0. And listen, this isn't just some neat little math fact. This is the absolute linchpin, the bedrock of Fourier analysis. The fact that these fundamental waves are orthogonal is precisely what allows us to pick apart any complex sound wave. Okay, so now we can finally connect all the dots. We have all the pieces on the table. Complex waves, this thing called a Fourier series, and this weirdly important property of orthogonality. Let's put it all together.
So here's the big insight. Because all those basic sine and cosine waves are orthogonal to each other, they kind of act like independent axes in a coordinate system. Think of them like the x, y, and z axes in 3D space. They don't interfere with one another. This allows us to use that inner product to basically project a complex wave onto each simple wave and perfectly measure how much of that simple part is in there without any of the others muddying the result. That's the secret. That is how you deconstruct any wave.
And that just leaves us with this one last big idea to chew on. This concept of breaking something complex down into a sum of simple orthogonal parts is one of the most powerful ideas in all of science and engineering. I mean, it's used in image compression, like how a JPEG file works, quantum mechanics, signal processing, it's everywhere. So it makes you wonder, right? What other big, messy systems out there could we understand better if we could just find their fundamental orthogonal parts?